Thanks, Mark. I'm going to start out by answering some questions that came from the first lecture. I was talking about binary systems involving white dwarfs, talking about novas. And somebody asked, well, why is it that if you have a material coming in at almost no velocity, how is it that you get angular momentum? Because they come in at no velocity at the center of mass. Well, you have to remember this system is rotating. First of all, this is a more highly evolved star. This originally was more massive, so it evolved more quickly. This is by now only about a half of solar mass, and primarily carbon and oxygen. It's the remnants. It's already blown off, or it's lost its outer layers. It's been a red dwarf already. And you can see now, because of the crossover point is farther from this star, this now has more mass. But this is now rotating about an axis out of the plane of the screen here. So when material is at this point, there's a force acting on it, the gravity of the white dwarf. So it's being accelerated. It's like it's falling from zero velocity, but it's being accelerated. When it starts to fall towards the white dwarf, though, the white dwarf is moving counterclockwise away from it. So from the perspective of somebody standing on the white dwarf, it's wrapping around in a circular fashion. So now it can't actually, so it's picking up angular momentum. It's like winding up a string on a top. It's gaining angular momentum. Angular momentum is the mass times velocity, momentum times the distance away from the center of the white dwarf. So it's gaining angular momentum. It collides with material that's already been arrived on scene, and so now it has this amount of angular momentum it's gained. It can't lose that. I remember talking to the first lecture about Emily Noether proved that the reason why the angular momentum is conserved. He was a great German mathematician. And so that's the reason, basically, that you actually start with no net velocity, but it's the gravity of the neutron, of the white dwarf, that's causing it to gain angular momentum until it comes into the disk. I learned something just in the last, early in January. There's a very great new ESA mission, European Space Agency mission. Astrometry is actually looking at the positions and the spectra of 1 billion stars in our galaxy. That's 0.4% of all the stars in the galaxy. It's still going to be operating until 2022, so there'll be more. And looking at a Hertzsprung-Russell diagram, looking at the distribution of the temperature of the star versus luminosity, they found a number of these white dwarfs were kind of stuck in one place, you might say, in the diagram. They're going to be cooling. They've been through the whole cycle. They're just a white dwarf now. There's no net fusion going on. They should be cooling over billions of years, but they found a number of them kind of static, not changing their position on this diagram for over 1 billion years. They're kind of collecting there. It's much like what's happening when you have water. It's being cooled. You start off with water at a few degrees centigrade or Celsius, and so for every calorie you take away from 1 gram of water, it cools 1 degree Celsius. But when you get to 0 degrees, it takes 80 calories, it's called the heat of fusion, to go from liquid to ice. There's net energy in liquid more than there is in the ice. I think that's what's happening here. They think that the actual, from the center outward, the white dwarf is crystallizing. So you can't go there and look at it, but it's behaving in the same manner as though it's crystallizing. And if you want to see more about that, if you look at the video or the PDF file, there's a link to that new information. To stay up in the field of astrophysics, you kind of have to look every day because there's always new things appearing. Another question that was asked is talking about neutron stars. Is it possible they should align over time? To be a pulsar, it's a lighthouse model. You have this neutron star rotating, but the magnetic field is at an angle to that. So when the poles of the neutron star, when the angle of the magnetic field rather rotates past you, you get pulses, radio pulses. And so one asked the question, well, would that possibly either align or anti-align over time? And it's a hard question to answer. One thing that happens, this is a picture of the sun's magnetic field. We can't really see the magnetic field at the boundary where the iron core is when it starts to collapse. When electrons and protons are combining and everything is collapsing, it suddenly goes from the size of a sun down to the size of a neutron star, 20 kilometers. And a lot of the particles that are still charged are being pulled together. It happens in a matter of seconds. So it's not very likely that in that process, everything suddenly co-aligns with the initial rotation axis. One interesting thing is, like, how many pulsars are there and how many should there be? If you look at the whole history of the galaxy, there should be about 100 million, or 10 to the 8th, neutron stars. And then, of course, they don't all beam towards it. So let's assume for now that maybe only 1 in 100 point in our direction. That's just a loose number, just pulled out of thin air to some degree. That would leave 1 million pulsars we should be able to see. But they have a finite lifetime, something like the Crab pulsar with a 30 millisecond period. Over about 10 million years, it'll slow down to the order of 8 or 10 second period, at which point the radio pulse mechanism breaks down. You don't find 15-second pulsars. And so that's 10 million years out of 10 billion years, the lifetime of the galaxy. So only 1 in 1,000 would still be operational. So instead of 10 to the 6th pulsars, you may have 1,000 pulsars. Well, what we actually observed is about 2,000. We see them from the entire galaxy. So something is taking away the lifetime of these pulsars. It's still possible it could be a change in the axis of the magnetic field over time, or it could be they're just turning off the mechanism, and it's hard for us to be sure. I did look for papers suggesting about what would be happening with the axis of the magnetic field over time. The papers are quite dated from the mid-70s. They're two good authorities, two good theoreticians. They came to opposite conclusions. So it's a little bit hard to, it's a little bit like archaeology. You have limited information, you take what comes your way, and you try to draw the right conclusions. But the likely possibility is that they just are losing their spin. They're spinning down, losing energy, and they disappear for that reason. So they probably have not, any alignment going on is taking place on a very long time scale. All right, one question, you asked this question of Jocelyn Bell Burnell, the discoverer of pulsar. She's going to be speaking here at the Rhinus lecture on March 12th. It's always a very popular lecture. You can RSVP. It's always a full auditorium. I recommend highly that you go to it. Kip Thorne gave the talk last year. So what I'm talking about in these 3 lectures, the first was the life cycle of stars and ending up with stellar endpoints. White dwarfs for stars that are about the mass of the sun or slightly more. If they're in binary systems, you can get novas and one type of supernova. If they're more massive stars, then they have core collapse, and you can end up with neutron stars and pulsars and black holes. So that was the topic of the last lecture. Today we're going to talk about the discovery of gamma ray bursts. What have we learned about them from observations? Why are they hard to learn about? And what are some of the major successes? And then the third lecture will be what are some likely causes of gamma ray bursts, and to relate to multi-messenger astronomy. Most of what we learned for astronomy comes from electromagnetic radiation, but now we have looking at gravitational waves and neutrino astronomy. Can we gain some knowledge of these objects from those 2 different channels of information? And ultimately, are they useful in understanding something about the history of the universe? Are the gamma ray bursts useful in that regard? I'm going to dedicate the talk to Steve White. Of course, he was Dr. White to me for many, many years. He was my thesis advisor. He was born in 1920. He just passed away this last March. He grew up in Kansas and went to a small college in Kansas, and he went on to get his master's degree at University of Illinois, Urbana. This is World War II, so he became a naval officer. He was quite a talented man, so he went to the Naval Research Lab and got involved in the Manhattan Project, trying to separate U-235 from U-238. Then after the war, he went to Berkeley and did work with things that produced the cyclotron there. He studied mesons, which are particles composed of 2 quarks as opposed to 3. Of course, that wasn't known at the time. So he got his degree in 1951 working under Edwin McMillan. And that same year, McMillan got a Nobel Prize in chemistry. He was the person who actually created the first man-made element, neptunium. He did that in 1940. So if you can't be a Nobel Prize winner yourself, it's good to work for a Nobel Prize winner. If not that, then work for somebody who trained under a Nobel Prize winner. So I was fortunate to work for Steve White. This is about what Steve looked like to me in the early 1970s, a very fit man. We used to take our detectors to Palestine, Texas to make observations. And you typically leave with a working detector, but it's quite a difficult ride in this old bus that we used. I'll tell you about that a little more in a second. So it's about 10 to 12 days of repairing, testing, calibrating, long days, 6 in the morning till late at night. And so every morning was started with Steve knocking on the door of the 2 graduate students, waking us up. And years later, I found out he was coming back after his morning run is what he was doing, very athletic guy. One time in the mid-70s, he and his wife came back from downtown Riverside, and as they arrived in the driveway, somebody was leaving his house. They were stealing, some thief, some burglar was taking something. And Steve jumped out of the car and chased him down the canal and caught this 19-year-old kid. He was about 53 at the time. He loved to tell that story. So then in 2011, it was the 50th anniversary of the department, and so several of us decided to get together. He had 17 graduate students over the years. I forgot to say that I left out part of the story. He went to, after he got his degree, he worked at Lawrence Livermore Lab for 10 years, and he was involved putting emulsions on rocket nose cones, and he was actually the person that determined the particles in the radiation belts were protons. He made that measurement. And then he worked for 10 years at Aerospace Corporation in Southern California, mostly classified work. He was the head of the Particles and Fields Division, hired most of the scientists there. And then he was enticed to come to Riverside in 1967. That's where I met him. I was an undergraduate there and taught an astronomy course. So three of the people in that class, myself and two others, either stayed or came back and worked for Steve. He was quite an inspiration to many people. At any rate, in 2011, there was a physics anniversary department, and so we took him out to dinner. I actually made the observations of the Crab Pulsar. I made a nice thing to make an award for him. I made a panel of thanking him for mentoring us and giving us great careers. So six of us made it back at that time. So he's 91 in that picture, very spry, still very capable. Whenever this other graduate student, Jim Ryan, who's now a UNH professor, came back, we always went up to Santa Barbara where he retired to see him. And he saw him as recently as 2016. He was doing very well. So he had a very long, productive life. We're lucky to have known him. So let's go back to the time of the 1950s we all remember, back to the period of Duck and Cover. I like this particular part of the film because I was a Cub Scout.
Here's Tony.
Have some more sound, please?
Tony knows the bomb can explode any time of the year, day or night. He is ready for it. Duck and cover. Atta boy, Tony. That flash means act fast. Tony knows that it helps to get to any kind of cover. This wall was close by, so that's where he ducked and covered. Tony knew what to do. Notice how he keeps from moving or from getting up and running? He stays down until he is sure the danger is over. The man helping Tony is a civil defense worker. His job is to help protect us when there is danger of the atomic bomb.
My 30 classroom had seats just like this, and we did this very thing. But then I remember pictures like this as well. I didn't feel very comforted by getting behind the wall. I also recall being told, if you see a bright flash in the sky, look away. And me, the budding scientist, said, isn't it already too late? So then in '63, when I was in high school, I was somewhat taken aback. I was surprised that we had a atmospheric test ban treaty. You see many famous people in that picture, Everett Dirksen, Johnson, Dean Rusk, and others there. And long before Reagan said, trust but verify, our country was doing that. So the Defense Advanced Research Projects Agency, DARPA, created some satellites with X and gamma ray detectors to be put into orbit to look for violations by the Soviets of the test ban treaty. And I'll tell you about how this worked. This is a case involving sources at infinity, a distance. I'll tell you why I'm talking about the case in a second. This chart's kind of low on this, I see. So imagine you have two satellites up, spaced by some thousands of kilometers, and you have a gamma ray burst, or you have something, an atomic bomb detonation coming from a certain direction, from an angle, some half angle to the axis of the two satellites. Then you first have the photons hitting one satellite and later another one, so you have a time delay. But you could see if you came in from an angle below the axis here, you'd have the same time delay. In fact, you can take this diagram and spin it around that axis, and it forms a cone or a circle in the sky. So you can't really determine the angle, just the opening angle of that cone. And so in this case, you have two satellites. You know that the detonation took place somewhere on this circle. But if you have another set of satellites, another third satellite, you have another axis, you have another circle. And so then where the two circles intersect, you have 2 points, either one of which could be the location of the burst. And of course, if you have a directional detector, you may be able to tell which of those two it is. So this has operated for many years, starting in the early 60s. And they actually had, a couple times a year, they had some indication. They had bursts that they observed. And they thought at first they might be the Soviets setting off rockets away from the Earth to hide where they were setting off these weapons and detonating them. So they were classified from 1967 until 1973. We didn't know about them at the time. So I'm talking about X-rays and gamma rays. I say a little bit about how we measure the energy. I'll be talking about keV and MeV many times. So an electron volt is the energy gained by an electron in falling through a 1 volt potential difference. So an X-ray tube in a dentist's office has a 10,000 volt potential. If you let the electrons hit an anode, slam into it, they'll generate 10 keV X-rays. Thermal processes can produce atoms moving fast enough that you can have a 1,000,000-degree temperature, you can produce keV X-rays. But much higher energy photons typically come from non-thermal processes, like the Compton effect, where a photon interacts with an electron, gives up part of its energy, and the rest goes off in a lower energy photon. Or pair production, where you have more than MeV energy, you can out of nothing create an electron and positron, as long as you can have a particle nearby to carry away the momentum. Or you can have magnetic field interactions. Anytime you have a particle, you change its velocity, meaning its direction or speed, you emit photons. They sound like big numbers, MeV, million electron volts, but it can remind you of the energy to raise 1 gram of water, 1 degree C, takes 4 joules, it's 10 to the 19th EV. So it's a big unit for a photon, but it's not an overwhelming amount of energy on the scale of humans. So this is the first gamma ray burst ever observed. And I saw this at a Friday colloquium in 1973 in the physics department. First thing we learned about it. And so these are 3 different satellites, labeled 5A, 6A, 6B. And this is a counting rate before the burst, about 60 or 30 or 25 photons per second. This is a logarithmic scale in time, kind of unusual. So notice there's a sudden increase to many hundred events per second, almost 1,000 events per second, seen in all 3 satellites. And by the time you get to just under 10 seconds, it's over. And you see the arrows are points that are common features of the rise and fall of the intensity. And so this is very exciting to us because I was just involved in '73 joining this gamma ray group. And if you can see a few times a year you see a burst, then perhaps with a large detector 100 times bigger in area or thousands of times bigger in volume, perhaps you can fly a balloon, detector in a balloon for a day or two and see gamma ray burst. But there was a problem with that, and I'll tell you what our problem was in just a few slides ahead. So these are some examples of gamma ray bursts. We used to say, once you see a gamma ray burst, you've seen one gamma ray burst. They seem like each one is unique. Some few things are in common. They have durations of tens of milliseconds to hundreds of seconds. They have some have a lot of structure, some don't have any structure at all. If you provide a sequence of these to a theorist, of course, you don't know how far away they are. That's a fundamental problem. Are these like a firefly an inch away? Or is this an atomic bomb 50 miles away? You don't know the distance, so you don't know the energetics involved. So you're just about nowhere as far as a theorist to try to identify the mechanism because you don't know the energy amount that's involved here. This is a typical spectrum of a gamma ray burst. They're kind of hard, meaning it doesn't drop very much in energy as you go up. This is 20 keV, a couple hundred keV. It's rather flat. You get about the same intensity here as you do at this energy, but then it falls more rapidly, called as a soft spectrum. So this is characteristic spectrum of a gamma ray burst. This is some more examples of the time scale of the events. You see some of them are tens of milliseconds, some are hundreds of seconds. So you start developing this zoo of examples, and it's very great confusion about what's causing them. So the high energy sky is very dynamic. At the first lecture I described the time scale of many things with stars is 5 billion, 10 billion years. Things are very static. Even a supernova, it tends to last, once it occurs, tends to last for a month or two. So the time scales are not the order of milliseconds and seconds. The high energy sky is much more dynamic. It's also the case, every time you go up a factor of 10 in energy, the brightest sources of the skies are different. So as you scan up an energy scale, the sky looks different every factor of 10 in energy that you go. So it's a lot to explain. And of course, it's also the case that these gamma ray bursts are occurring at random times and random locations in the sky. You can imagine if you could see gamma rays with your eyes, there'd be a flash somewhere in one location and then somewhere else entirely. How do you design an instrument to look for that? And that's why it was so hard to get observations for such a long time, because focused instruments you're going to see almost none of them, And plus, you actually can't really focus gamma rays above 10 or 20 keV. So you have to think light buckets. You have to have shielding to keep things from looking on the outside. And you can only look at maybe a 500th of the sky at one time. You can't capture them. It's just a random thing. You're looking for a target of some type. You might be fortunate to see a gamma ray burst in that location, but you don't see very many of them over the long term. That's a problem. So what do you do to see gamma rays? Now, in the radio spectrum, down the shortwave band, you can bounce signals in the ionosphere. You don't see past the ionosphere. In the meter band, you can see all the way from ground antenna to space. Even in the optical band, the same amount of energy that's coming in from the sun, it doesn't all make it to the ground. And the atmosphere is opaque in the X-ray and gamma ray range. It's good for humans, but bad for astronomers. So you have to get above that. If you take the 1 square centimeter on the ground and you add up the amount of mass all the way from ground level to the top of the atmosphere, it's about 1,000 grams. And MEV gamma rays only get down to about 3/1000ths of that. So you have to get way above the atmosphere, all but 3/1000ths. You have to get up 25 miles above the atmosphere in order to see gamma rays. And that takes a lot of work. This is what's getting involved here is the early newsreel from 1960.
Air Force balloonist Captain Joseph Kittinger, Jr. is laced into an elaborate pressure suit in preparation for a daring ascent into the stratosphere. Kittinger, who weighs 150 pounds, packs 155 pounds of suit and equipment. The scientific goals of Kittinger's ascent are to test a new 6-foot stabilizer parachute designed to keep an ultra-high altitude jumper from spinning and blacking out before he can open the main chute. The balloon reaches a height of 19.5 miles.
I didn't do this. These are unmanned balloons with data telemetered back. So, as I mentioned, there was a problem in 1973 being able to make observations because in 1971, the group of graduate students before me had a catastrophe. They, against the protests of Steve White, their payload was cut down, terminated through a thunderstorm, and the parachute got emptied by updrafts, and it free fell from 30 or 40,000 feet and was destroyed. So I was back at the loading dock of the physics department when they brought that back. It's a big payload. It weighs 1,500 pounds. It's about 6 feet in diameter, 7 feet tall. It consisted of 2 large tanks of liquid scintillators. Scintillator is a material that, when gamma rays interact, the electrons are given energy. They fall to the ground state and emit UV or visible light, which you measure with the Fulton multiplier tubes. But the point is, these tanks leaked. And the tanks were surrounded by plastic sheets to detect charged particles, because you don't want to measure the charged particles. Well, the liquid scintillator dissolved the plastic scintillator. It looked like a cave of stalactites, all these gooey things hanging down. And everything inside was destroyed, nothing bigger than a square inch. In fact, you had integrated circuits, like 14-pin, 16-pin devices. All the plastic caps were off. A lot of the leads were broken. It was totally destroyed. So we're in a rebuilding period at this point. Now, one thing that was really important to scientists is having really good engineers. And we had an excellent electronics engineer. He'd worked for the aerospace corporations where he'd have one small part of a project. And he wanted to work everything by himself. These are very competent people. They wanted the responsibility. They had the expertise. They can do it all alone. It was something to watch this person work. So he did the entire. This is a time when it was just becoming possible. There were not, computers to fly in these packages. There were, intercoupled logic, T-squared-L logic, and you had to do this all within 100 watts. So it took a lot of very clever work to design a system that could collect these high-speed, microsecond-long pulses from the gamma rays interacting, and go all the way up to adding them up in different energy and time bins, forming the data stream and modifying the FM signals and sending the data back. It was quite a job to do that. And so he would do this design, the whole system, in we had about a 4-foot by 6-foot panel and pencil, and then to break up in pieces, and graduate students, technician would build them all. I remember walking into the lab, he'd be looking at prototype circuits, and there would be a signal he'd be looking at with a scope. It was supposed to be stable. It would be oscillating. He'd reach over to the bin and find a 0.1 microfarad capacitor and clip it in place. It would suddenly become stable. I'd say, Wayne, how'd you know how to do that? He'd chuckle and say, oh, experience. So these people are so valuable. There came a point in this, our operations there where we really couldn't afford to keep you anymore. We only were making minor modifications. And the day we discovered that Wayne was leaving us was a horrifying time for the remaining poor, pitiful graduate students that had to carry on. So we also had such an excellent engineer, similar guy at NASA, at Marshall Space Flight Center, that they were interested in the science. They came out with science lectures, and they did all this work, and they were just, you learn that people, you really rely on these people. For a while, between college and graduate school, I was doing civil engineering work, designed roadways to widen them for heading into freeways. And you did the work, you laid the grades, you made sure the driveways didn't catch cars didn't get stuck on them as they left the roadway. After you did all that work, they were checked within the squad, the local room there. After that was done, they were sent off to the checking squad, the people that were most experienced. There was so much checking going on. But it wasn't that way at NASA. You had individuals that came up with the designs. We tested them. There were just a handful of people. There was no other layer of checking. There occasionally was a critical design review, but really it wasn't a depth of analysis. So people realized that it was up to them. Of course, we wanted to succeed. We were counting on getting data from this, and the people, the engineers, were in support of that. But you really recognize when you're doing this work, if you do it wrong, nobody's going to get anything, and that's very motivating to people. So after a couple of years, we finally managed to get our detector together, and this is the way we transport it. It's not the actual bus. Because we had funding from Naval Research Lab, we managed to get an old Navy post bus, about 1960 vintage, and they cut the entire back end off here and hinged it, took all the seats out except for a couple plus a driver's seat, and loaded everything in this bus. It had a very underpowered engine. You could stand between the inside fender and the engine. The engine was tiny inside the opening up there. And it was very, very underpowered. If you're driving down the road, it would start to slow down. It says, oh, we must be on a grade. Like a 0.5% grade would start slowing down. You want to go about 25 miles an hour or a place like the Cajon Pass. So finally came the morning in 75, we got on the road, and we're heading towards the California border. I was driving, and you see all trucks exit here. It was an inspection station. So we debated, are we a truck? Should we stop? We're in a Navy vehicle. We don't have any Navy papers. We don't have any papers of any kind, So I said, well, I think we better stop. So we stopped and pulled up at the appropriate point with the stop sign. I got out, went into the fairly large office and talked to the guard. Oh, you don't have to stop, it's okay. So I got back in the vehicle and started to pull away. When I heard this guard shouting, I looked in the side view mirror, and he had his gun drawn. He said, well, it's bad for me and bad for our experiments. So I got out and said, oh, I didn't realize you're allowed to go. So that was a very memorable moment. On another trip, we had a successful flight. This is Bruce Dayton. He was also a UC Berkeley man. And we were calibrating at Cal State LA on another occasion. And we're going down the road, and Jim Ryan, my fellow graduate student now at UNH, said, Bruce, we're not alone. And Bruce looked down next to his hip, and he saw this. Oh my God, a 10-inch centipede, we assume poisonous centipede. So he managed to bring it to a halt on the side of the road. Well, he opened up the lever to open up the doors. We exited, and there was a piece of tire there. So Bruce grabbed the tire and turned it into liquid forms. It got rid of it, so unforgettable experience. Okay, so I'm going to show a 7-minute video here about what it's like to the people that actually do the balloon launches. They'll talk here about some launches, some missions that can last more than just a few days. That's capability they've gained since the early 1990s. Back in the day, we were doing balloon flights between 75 and about 1990. Most you could hope for is about 3 days. So I think it's an interesting video to watch.
It's been called the quiet workhorse of space science, a means of transporting ambitious and hefty scientific experiments to the edge of space.
We're gonna start inflation at this time. Everybody got earplugs that wants them?
While the technology may seem old-fashioned, it remains the quickest and most cost-efficient avenue to near space.
When you compare to satellite missions that take 5 to 7 years to develop and millions of dollars, scientific ballooning can be done on a fraction of that budget and in a fraction of that time.
From the study of the atmosphere to the origins of the universe, it's been the vehicle for some of the most significant scientific discoveries of our time. And the future holds even more promise for one of the greatest scientific stories never told. No one launches more scientific balloons from more places around the world than NASA's Columbia Scientific Balloon Facility, based in Palestine, Texas.
The strength of the program is that we can fly very heavy payloads, up to 8,000 pounds, and very large payloads. We can put those experiments into near space above 99.5% of the Earth's atmosphere.
The scientific balloons they use are made of an incredibly thin polyethylene film, only 0.02 centimeters thick,
8 mils.
the thickness of an ordinary sandwich bag. They can fly that 8,000-pound payload, the weight of 3 small cars, nearly 23 miles high, to an invisible ceiling where the atmosphere ends and space begins, and can stay there, riding upper atmospheric winds, for up to 6 weeks. Due to the natural difference in density between the helium gas used to fill the balloons and the air, as these zero-pressure balloons ascend in the atmosphere, they expand to volumes of up to 40 million cubic feet, nearly the size of a stadium like the Louisiana Superdome.
But to launch those into space would take a very expensive launch vehicle. I mean, really, literally only $100 million for the launch. And whether we do these for, certainly 1/100th of that or less.
And we can have greater access to space, more frequent flights of science, and in the end, the scientist gets their payload back.
From New Mexico to Arctic Sweden and Australia to the coldest and driest continent, Antarctica, the Columbia Scientific Balloon Facility launches 15 to 20 balloons a year over 4 to 5 campaigns.
All right, guys, we're ready.
Locations are typically dictated by science or longer data gathering air time.
Any science that can be done above about 99.5% of the Earth's atmosphere, either looking up or looking down, can be done on balloons.
The scientists using scientific balloons include some of the world's most seasoned researchers and university professors, even graduate students.
The young scientists can design the experiment, build the experiment, fly the experiment, and analyze the data, go through all aspects of a space mission, which is not possible with our large space mission.
And ballooning is a vehicle for world-class science. In the mid-1980s, an ozone hole was discovered over the Antarctic continent. The initial measurements were all made from scientific balloons. Another high-profile balloon-borne experiment called Boomerang in 1998 showed the geometry of the universe is basically flat and continually expanding, a finding consistent with the Big Bang Theory. And in 2003, a cosmic ray experiment called CREAM orbited the South Pole 3 times, setting a long-duration scientific balloon record of 42 days at float.
15 years ago, this capability would have been unheard of, and we got quite a bit of attention in the science community from people who are interested in these extended duration flights.
Getting beyond the atmosphere by balloon involves handing complete responsibility for the scientific payload and launch to the Columbia Scientific Balloon Facility crew.
So I'll be communicating with you all the time during that.
While there are subtle rigging differences from launch to launch based on specific scientific needs, whether launching from Sweden or here in Fort Sumner, New Mexico, the main layout of a typical scientific balloon flight train is essentially identical. This hands-on rigging remains one of the most complex and critically important processes.
We'll set a show time, we'll come out, we'll hang the gondola, then we'll go out to the launch pad.
It begins with the pickup of a scientific payload with a specially designed launch vehicle.
And attached to the payload will be suspension cables that will go upward to what we call a truck plate. That truck plate is actually holding the entire flight system to the launch vehicle. From that truck plate, there will be a suspension ladder that will go over the launch vehicle, and that will connect down to the parachute separator unit.
Rotator should be on.
This unit separates the parachute from the payload to prevent a wind-filled parachute from dragging and damaging the payload after termination. The nylon parachutes range in size from 46 feet to 159 feet in diameter for the largest payloads.
And then we'll have the terminate fitting, which is the link between the parachute and the balloon. That terminate fitting will have an explosive device on it that we'll initiate to bring the balloon down at the conclusion of the flight. And then connected to the terminate fitting will be the balloon itself. And on top of the balloon will be helium valves that will open at the end of the flight as a secondary measure to terminate the balloon.
This is one of our flights in 1982. We like doing launches from Palestine because they have this special equipment. When you're off in a remote site, they're using a modified crane. The device they have in Palestine actually has generators running the drive wheels. They have not running the drive wheels, running the electric motors. So if you have a stumble from the engine, you don't have any stumble in the motion of the equipment. So you have to worry about that. The time to fill a balloon takes about an hour. And what you clearly don't want to have is a change in the wind direction once you start filling, because then you have to have maneuverability. You have to get underneath the balloon once you release the bubble. And so some things don't always go so well. I did see one attempt to launch a 52 million cubic foot balloon, and it turned into 70 acres of plastic. It's always, when you're there preparing for your balloon flight and you go out to see somebody else's launch, it's always very discouraging to see, instead of a flight, see a pile of plastic. You hope you aren't the next one up to have that happen to. This is an especially beautiful launch, I think, that went very smoothly. First of all, you notice up here on the top, this is a patched balloon. That's something else that really worries you as experimentalists, because you have to rely on that patch, not just for the launch, but the entire 1 or 2 days at float altitude. So you really hope they patch the balloon very well. So you like to have an intact balloon. So this is a patched balloon. A lot of stresses on the balloon at this point. There's almost no wind in this case. So much so they have to actually back up to do the release.
Colors away.
Notice how hard you have to pull to release it. Woo! The excitement is because it doesn't always go that smoothly. So that's a picture taken at float. You see it's expanded into its natural shape. You can see the suspension of the package underneath it. So these are zero pressure balloons. So they go up to float altitude, but at night the sun is hidden, of course. The atmosphere cools off and they start descending, and they have to drop ballast, maybe 400 or 500 pounds of ballast, to stay at the float altitude. You don't want to come down because it starts attenuating your signals. So the next day, when the sun comes back, you go even higher and gas leaks out. So after about 3 days, you're out of ballast and you have to cut them down. Things don't always go so smoothly, and here's a little report about that.
Some of NASA's latest space dreams came crashing down in Central Australia today. A giant helium balloon packed with expensive scientific instruments lost its moorings in high winds. As Anna Henderson reports, it cut a swathe through an airfield and sent onlookers running for their lives.
As the giant helium balloon was launched into the air, its precious cargo became a high-speed projectile. Unexpected strong winds pushed the 2-ton platform of scientific instruments off course and onto a path of destruction. Justin Trotter's car was tipped over. He can be seen here running for his life.
They started losing control of the payload. We started to move the cars and just barely made it out without getting smashed.
The couple sitting inside their vehicle right next to his car can barely believe they survived.
There was just lots of noise and we really thought we were gone.
It was just an instance of chaos outside. We were expecting to be wiped out.
While Justin Trotter was inspecting the damage, NASA scientists were picking up the pieces of years of work. It's not clear whether anything can be salvaged.
Everybody is feeling very down about it. A quick look showed that there were bits that were in pretty good shape. But to be able to expect that to be put together within a month for another launch seems unlikely.
The Glad-wrap thin, giant balloon came down in a nearby field and will be thrown away. The balloons are launched into the stratosphere carrying cutting-edge telescopes that help give astronomers and scientists a much clearer view of space. Organisers say they are relieved no one was hurt.
So I read the accident report that came out about a year later after this. So what went wrong here is, you saw how hard it took to pull that lanyard to do the release. So they pulled the release and they couldn't get it released. And so they came to a stop with the crane, the launch vehicle, at which point the balloon's getting ahead of it. Then they tried to accelerate again, and they're having trouble with traction off the end of the runway. And then spontaneously, what they should have done is cut away the balloon and have it be a failed launch. But the package suddenly released on its own, and it's way back behind where the balloon is. So it ends up dragging onto the ground, at which point they did cut the balloon away. But people used to think the risk of ballooning was only when they come down at some location that's unknown. But so they've changed their procedures. They don't let people out of the village come look at these launches and stand anywhere they want to anymore. They take more precautions. But the release mechanisms they use on the cranes they have at Palestine, Texas, are spring-loaded. They don't suffer from this. So if they lubricated that where the truck plate was in that pin, this would never have happened. Well, I was on a recovery one time. My first balloon flight, actually, they let you go off in a chase plane because you have to then, after they cut it down, then you have to go safe to experiment, take off the batteries and so forth. The very first time I was in that situation, so you're in the plane and the pilot says to you, "Can you see the package?" Well, you're looking up 25 miles away. Pilots are good at finding things like that. After a while, "Oh yeah, I see the balloon." So he gives a cut down command, and then you start noticing that there's a balloon and a package, and they're falling at the same speed for several minutes. Of course, then the pilot says, "Oh, it looks like a free fall to me," teasing the young graduate student. Of course, there's no air up there. It takes maybe 10 or 12 minutes before the balloon finally falls faster than the parachute has some effect, and you start to notice that maybe you're going to have a package after all. So another occasion, we had a balloon flight that was launched from Palestine, Texas, and we actually had a downrange station in Huntsville, Texas, and it headed up towards Roanoke, but it was late at night, heading towards populated areas. And so at midnight, because they didn't want to go more populated areas, they gave the cut down command. And we didn't know, of course, where it came down, so we went to sleep. Next morning, got up, put the news on, and there's pictures on the news of our package. And it landed in the middle of a creek, a very shallow creek. It didn't do any damage. And so we managed to find where its location was. And there was a small trailer community around that. It landed within probably 80 or 100 feet of trailers. And all these people hangers-on looking at this, I think they felt we put the package down right in the middle of the creek on purpose. You know, there were no angry people. I would have thought the citizens might be up in arms with pitchforks, but they were perfectly happy. So before the launch of GRO, what was the state of knowledge about the location of gamma ray bursts? And you see it was not very good. They're only about 2.5 per year. In all of the 25 years since the discovery of gamma ray bursts, this is what you knew about their position. This is galactic coordinates. So the center of this plot is looking at the center of the galaxy. This is 180 degrees west longitude, 180 degrees east longitude. This point and that point are the same. This is north latitude, south latitude. So this is the whole sky. And we wanted to see, is this something that's a galactic phenomenon? Like you see the Milky Way galaxy, you'd see a plane right in the middle. Or are these coming from somewhere else and you'd see something equally distributed? Well, what's the distribution? Nobody knew. I went to a conference prior to the launch of GRO, and they actually gave out badges to people when they checked in, you know, cosmological or galactic. And it was about 50-50 because we'd just be guessing. Nobody really knew what it was. And so the goal of our experiment was to do a mapping of many, many bursts much more accurately and find out, are they a galactic phenomenon or are they extragalactic? That was the goal of our experiment. So we launched, this is 1991, we finally managed to launch it. We thought it would be much sooner. I mean, I came to Marshall Space Flight Center in 1978, expected within 4 or 5 years to be able to have this experiment launched. But there, of course, the Challenger action was part of the delay, and just building the experiment was part of the delay. So it was a bold mission by NASA, and thank you for the taxpayers, across the whole spectrum to be able to look at the factor of 10 improvement in sensitivity, all the way from the infrared, visible, X-ray, and gamma ray. The Space Infrared Telescope actually became the Spitzer Space Telescope, Infrared Telescope, Hubble Space Telescope, Chandra X-ray Telescope, and GRO Telescope. There's a story to tell why it's not still flying. I don't know if I have time to tell that or not, but it was a very once-in-a-career opportunity to have an experiment on a satellite. So that was really a wonderful thing that we managed to be selected for that, and good for the science. So I say our main goal was to determine the directions to a large number of bursts and what's the sky distribution, and secondarily, do they repeat? And also study other sources, X-ray pulsars, X-ray transit. I don't have time to talk about that work here, just the bursts. And so this is clearly not just my work. I was the third person to show up there, but by the time at the end of the mission, we had 14 scientists, 3 postdocs, 4 graduate students, to 3 data techs. We had a couple women scientists, so like 20%. Right now, the successor mission to the BATSI experiment is on the GBM. It's on the burst monitor on the Fermi telescope, and the young woman who came as a co-op to NASA, where they go to NASA half the year and trained in college half the year. She's now in charge. She's the PI of that experiment. So let me describe a little bit about the detector. It's a really simple detector. So first of all, we don't want to be involved with measuring charged particles. So out in front, first of all, the particles coming from all directions. We're going to care about the ones that come from the front because we're going to look at different detectors having different counting rates and tell what direction the burst is. But the actual events are coming from all directions. When a charged particle goes through, it gives a signal from this thin detector in front, and we veto. We don't count those signals. But there's a plane here with a large area detector. It's just a 20-inch diameter, half-inch thick piece of sodium iodide. And when a gamma ray interacts in that, it gives energy to electrons. They fall back to the ground state and emit a flash of scintillation light in the UV to visible range. And that light bounces around inside this cone. It's sort of graphically, it's bouncing around in this cone and exit into these 3 apertures with there's photomultiplier tubes, and they get converted into pulses and we measure them. This is happening for every single photon within a microsecond. We're counting every single one individually, and then we add up into various bins. This is the principal investigator, Jerry Fishman, who had the concept of the experiment at the beginning. So once again, these are the photomultiplier tubes and their magnetic shields at the back. It's not a beautiful detector. They actually added some of these things called bathtub fittings here to give it more strength. I can tell you that the designer of this detector, of course we built them out of sheet metal and plywood for the balloon flight. It's a different environment entirely. His name is Joe Smith. He actually is a person who designed the hold-down bolts that holds the shuttle in place while the shuttle main engines are developing thrust before the SRB. So he handles big, bulky things. So he did a great job, and it did work. Okay, so the phonomultiplier tubes, this isn't really important for you to remember. There's a story that goes along with this. But some of the photons, like 1 in 5, the UV photons, knocks an electron off the interface of the phonomultiplier tube, and there's like 300 volts accelerating that towards a dynode, where it knocks off 2 or 3 electrons. Then they're accelerated to another dynode, where they each knock off 2 or 3. And this keeps on going for as many as, I think we had 11 stage tubes. By the end, you have enough electrons to actually collect them on a capacitor, measure a voltage, and you can come up with a measure of the energy input. So if you have a higher energy gamma ray, you get more UV photons and a bigger voltage pulse. And this is how you're making the measurements. You see you apply high voltage up to 2,000 volts and get a million amplification. This is just a picture of the photomultiplier tube. It's in a bag. It's causing that line across the image there. And the back end of the tube has this neck here. And there's a reason for telling you this detail. So we ordered these tubes from Thorn EMI Gencom. They've been manufacturing since World War II. They're the premier company that built these things. And they seem to be falling behind in deliveries, like they hadn't delivered any. So Jerry sent me to England to investigate. So after a long overnight flight, I showed up at 10 in the morning there for the meeting. And they hit me with the fact they were having trouble making these tubes. These had been made for 10 or more years in different satellite missions. They're having a problem because they were producing particles in there that were conductive. They were actually slightly smaller, slightly larger than the spacing between these dynode elements. And of course, that would, if you short out a stage, the gain's down by a factor of 3, and you don't have what you want to do. So they were presenting with making a decision. This meeting went on for a while. They brought out a nice catered lunch, a bottle of red wine. I turned out later, I said, you shouldn't take gifts like that more than $5 from a contractor. I didn't know I was in violation. But I said, I've had no sleep. I'm not making a decision. I'm going to get some sleep, come back tomorrow, which is what I did. So what we agreed to do, since they were making some tubes that were satisfying the conditions, we'd stretch out the delivery schedule, have them screen the tubes, and send us the ones that didn't have a problem. That was my decision. So we did a lot of testing. This is, you can tell it's an old picture here because of the 8M3A terminals that we built from kits. And this is a frame here with running currents through for Helmholtz testing for looking at magnetic field sensitivity. And so we did an awful lot of testing. So we had this one person, William Hammond, that went back to the Apollo days, actually probably before, and we gave him the job under a 20x binocular microscope to take each of these tubes. Oh, I should have said, when I was at EMI, they gave me a factory tour, and they showed me the assembly process. It took about 10 weeks to build these tubes up, a lot of spot welding inspections. It was all women, hands-on work, doing this fine work, and all the inspectors were men. I bet the men got paid more, which is just totally wrong. So anyway, so you got these tubes delivered, and William would spend several hours on each tube. You see the front face, it's sort of this brownish color because it's partially covered with this photocathode material. It's hard to look. And looking into the side of the tube, looking back here, it's hard to really do a good job inspecting this curved glass surface to see what's underneath. So he'd look for many hours, and he'd occasionally say, Bob, I think I found one of these particles. I'd come look and say, yeah, William, I believe you did. So we returned fully a quarter of the tubes they delivered as being acceptable. We sent them back. They never bounced them back to us. And so then, long after the launch, you kept worrying on a linear basis, are we going to have tube failures because of this problem? And we went on for month after month, year after year, with no failures. So by this time, he was on other projects. So whenever I passed him in the hallway, I would always thank him, William, you really did your job. So that NASA was full of people. There have been major cuts in the staffing at NASA after the Apollo landings, and maybe 40% of the workforce was cut. But some of the really best people, machinists, engineers, technicians, the best of the best were the ones that were left. And you could really count on them. You can give them a job to do without much supervision, tell them what the job was, and it got done correctly. And it's an amazing, something the scale of a satellite project. It's not just at NASA, it's at the contractors as well. That you actually can have something designed and fabricated and tested and have it work. It's just remarkable to me that you can make that work. So how do we get the directions to the burst? Is by looking at the relative count rates in different detectors. So in this particular orientation, because you have a greater exposed area, this detector would get more counts than one of these down here, for example. And for bright bursts, you get a direction to within maybe a few degrees circle. And for weak events, right near threshold, it may be 10 or 15 degrees circle, not very accurate. But that's the nature, that's how the experiment is working, is by looking at the relative counting rates of the different detectors. There's this problem of scattering. This is an example of this from looking at the sun directly or scattering off a water surface. The actual case for on orbit is a little bit different. The worst case for scattering is actually large angle scattering. So if you have a case where the burst direction is giving you direct photons from above, the ones that scatter off the Earth and go into the back side here can give you a false location. So every time you do a burst location, you have to look at the relative counting rates, calculate a crude position, and look at see if the scattering makes sense and iterate. So it's quite a complex process to deal with all this. You can imagine you've got a small 20-inch detector, and you have the entire Earth's atmosphere below you. It's a large scattering. By factors of must be 100,000 more area that can scatter into you. So it's quite a difficult problem. You have to know your scattering physics very accurately. We had one person that concentrated on that work. So finally, on April 4th, 1991, we had the launch of GRO, renamed the Compton Gamma Ray Observatory. I was down there for the launch. It was exciting and worrisome.
Liftoff of the Space Shuttle Atlantis and the Gamma Ray Observatory.
Yeah, this is sure a pretty sight, Marche. It's just gorgeous spacecraft they've got here with this beautiful black wing.
So this is I won't have time to describe the other detectors. Maybe just briefly, there was the Egret experiment, looking using the pair production to detect higher energy photons. The Comptel experiment, looking at 30 to 200 keV MeV gamma rays using the Compton effect. And the OLLI experiment, looking at the same energy range as us, but it's shielded, so I looked at a narrow part of the sky and looked on source and off source. So we have 4 detectors parallel to the octahedron on top, and 4 you can't see on the bottom. Oops. So there was a problem. When they gave the command to deploy the high gain antenna, it didn't move. There's a parabolic dish right here. In spite of, you can do all the testing on the ground, but you're not in zero-G conditions. So in spite of all the money spent, I'm sure they spent $1 million designing and testing that, it wouldn't come out. And if they had to bring the payload back, then they probably would never have reflown it, because the amount of retesting it would take and requalification, we felt that would be the end of it. So it was a very, very stressful time, not what we were hoping to see. And so Jerry Fisherman and I were sitting in a room that had a large HD TV, not very common in 1991, and watching the astronauts do their work, and I found a press conference after the fact showing what we were watching.
Well, as Ken said, we had thoroughly trained to be prepared to react to spacecraft contingencies such as this, and we were out on the spacecraft very quickly, surveyed the situation, did not see anything that should have been causing the boom to hang up, and with some relatively easy force inputs were able to jostle the boom free. Analysis now says that probably there was just a little bit of thermal cover on the boom that was hanging up on some of the spacecraft structure. I think at this point I yelled gleefully, "It's free, it's free." As far as I was concerned, when that boom came free, that made my flight for me. It was the only reason that we went on this spacewalk, and with the successful freeing of this boom, we then translated over to the other side of the spacecraft, where Jay and I completed the task of putting the boom into its on-orbit position. You can see I'm in a foot restraint, and Jay is supporting me and watching my legs to make sure that we don't do any damage to the spacecraft as I very slowly and gingerly raise the boom up to its full deployed position, and then with a wrench was able to drive a mechanical system over center which locked that boom into its on-orbit position. Then Jay and I quickly left the spacecraft so that the POC could turn on the spacecraft's transmitters and receivers and fully check out the spacecraft in preparation for release. And during that time, both Jay, as you see here, and me in the other window had a chance to come up and say hi to the folks inside and see what they were doing. I think they were eating at this time, Jay, if I remember right, while we were outside working. We're saying hi through the window to them there.
Well, some point after that, matter of fact, it was a good bit of time later, the arrays, we moved it back up to the release position. The arrays were fully charged. The POC finished testing out all the systems. It looked really great. We were ready to release grow, which we do by opening the snares on the arm and very carefully backing away so as not to provide any rates on it, although a 35,000 payload is pretty stable up there in space. That's what.
Okay, so why don't we take a break here, Mark? Ready? Okay, so I got to ask one question. I forgot to say something. This is the plot that showed the knowledge of burst locations before we flew the Gamma Ray Observatory and the BATSI experiment. Oh, I don't have it on here. Okay, very good, thanks. What this chart shows is there are a few boxes that are actual locations on the sky, things are well determined, but many of these things are arcs. And what these are is much like I showed you the veil of spacecraft, where you can locate a circle in the sky with two spacecraft, that the burst is coming from somewhere within that circle. There was an experiment at Venus, Pioneer Venus Orbiter, and along with a spacecraft near the Earth, and all you get is a big circle in the sky. It's very narrow because you have very good timing, but all you know is it's somewhere on that circle, so it's clearly not localized. And fully, almost 10% of the sky is covered by these regions. So there's really not much information at all about the locations. Let me step ahead here. Maybe I should go back and do it here. Okay. So these are the greatly appreciated astronauts who succeeded in pulling out the antenna. So it was a very suspenseful time. So we got through the launch environment, but we didn't really know for sure what we had because I had to wait 10 days because you want to let any outgassing take place. You don't want your high voltage to fail because the residual gas is somewhere in the system. So we had no knowledge other than temperature measurements of what we had on orbit. So then we knew what we were going to expect for counting rates. It's going to be a little bit different than on the balloon altitudes because there's some cosmic diffuse gamma ray background that's very soft that doesn't penetrate down to the 3 gram point in the atmosphere. So when you go above that into orbit, there'll be some softer emission to increase your count rate. And then then you have to account for that. We raised our thresholds to account for that. But we had a pretty good idea of what backgrounds to expect, about 5,000 counts per second. So what we did is we turned on just a single detector, a command sequence just for 5 seconds on and off. And we saw the expected count rate, which is just wonderful. And so then we turned all the detectors on sequentially just like that. And so we actually had working detectors. All 8 detectors were working. So in the balloon flight era, we worked for a whole year to prepare detectors, took data at the top of the atmosphere for 1 day. And now we were looking at the entire unclouded sky every day. It was just fantastic. So every day we get a news day's worth of data from anywhere a few hours old to a little more than 24 hours old. And we had automatically generated plots. So every day you could come into the operations area and see 8 plots on different energy ranges. And we're looking at the whole sky, except for what's blocked by the Earth, every single day. It's a feeling of empowerment. We're looking at everything that was out there continuously. Now, we don't send back high rate data for every, we can't afford to do that. We're actually looking for signal rate increases in 2 or more detectors. We capture data at a high rate for a couple hundred seconds, and then dribble that data back over the next 90 minutes over in orbit. So we're capturing the data all the time. But we're looking for triggers to capture high rate data and then send that data back. I think we had 35, 55 bits per second was our data rate. We had higher data rates in the moon flight days. We collected, it sounded like out of data at the time, 40 megabytes a day. Doesn't sound so big anymore. So every morning we'd come in, on weekends we did some processing for home, but we didn't report it until the following Monday. We had anywhere from 0 to 12, very rarely we had no triggers, as many as 12 triggers in a day. And each person, somebody was assigned to take the data that was pre-processed, run additional analyses, and come up with an estimate, was this a gamma ray burst or not? Because there's other things that cause triggers. There's electrons precipitating in the atmosphere. They can either be local, actually in the spacecraft, or on the horizon. It could be solar flares. X-ray transits can go off. You can have really bright sources on the limb of the Earth. So it's basically kind of like a jury. You make a presentation with your evaluation as to what the cause of this is, and you have the evaluation of the other experts in the room, and you reach a decision. It's a very important decision because it's subjective. You don't have any absolute ability to decide what this is, and it's crucial that you not include things that aren't gamma ray bursts in your distribution. So it was treated very seriously. It was passed around from person to person. I know in the current mission, the gamma ray monitor on the Fermi satellite, they're actually using some Bayesian analyses, actually done it more of an AI approach to decide what this is, so they've improved the techniques. But I think that we did a good job. We actually would have guests come in. We were not exclusionary. Anybody that was in town visiting us, we pulled them in to actually be part of the process. So it was a very open process we used. We knew it was crucial to do correctly. So we were launched in April, and by the end of the year, since we were seeing about 1 burst a day, we had enough bursts to say something about the distribution. Like I say, the previous 20 years we had 60 bursts, and now within, we had enough we had outnumbered that. In 2 months we had more than that. So we made the cover of Nature magazine in January of the next year. And I don't have the data in that paper, but I have what we had at the end of the mission. And what we had was a distribution that looks a lot like the cosmic background radiation. So this is, once again, the galactic coordinates. So it's west longitude 180, east longitude 180, plus or minus 90. This is just different brightness bursts. It's ergs per centimeter squared integrated over time. But for every one of the subdistributions to within a percent order, they're coming from all directions equally. So this says either you have bursts that are very nearby and homogeneous and coming from every direction, or very far away. We don't know the distance scale yet. We're still missing the distance information, but it's highly suggestive that it's not galactic, but it's not a certainty. And I'll tell you how we can get some information about that just ahead. So all the other gamma ray sources are actually planar. They basically form like a Milky Way distribution because they're part of this galaxy. So this is the fundamental measurement that we're trying to make with BATSI. We're successful in doing that. So let's describe how you can get some information about the distribution. This is slightly complicated, so let me slow down and describe that. Let's consider a distribution that's uniform in space over some large distance scale. This is the blue dots represent the distribution of gamma ray bursts in space. We're at the center of the diagram. And so for a given radius we pick, the number of burst sources at 4/3 pi r cubed times the density. And if we go to a larger radius, maybe double the radius, it's proportional to a larger radius, so it's twice as large. It would be 2 cubed or 8 times as many sources. But they're dimmer to us because it's 1 over r squared effect. They're only 1/4 as bright. So what we're going to do is we're going to go for every possible size measurement, how bright they are in a detector. We're going to count how many bursts are that size or greater. We're going to do an integral distribution. And if we're still within, this distribution continues indefinitely, we should get a -3/2 power law. The +3 comes from the increased volume as you go down to weaker burst, and then 1 over r squared comes because they're farther away and thus dimmer to you. That's the technique. It's a log n log p distribution that we're forming. So most people are very familiar with histograms, the differential type, which we see here. So we just plot differentials. This is pulled out of some other paper involving volume and dose of something. And so if we ask how many bins, what's the contents of the bins that have doses greater than 120, the answer is 0. Or what's the volume contained in all doses greater than 0? We add up all the bins you see here, and we get 100. It has to be normalized to 100. Or we say, how about at 80? We add up everything to the right of 80. So we're looking at the integral distribution. You can see if you could check yourself, because where the slope is least here, we have the smallest value. And where it's steepest, we have the highest value. So the point is, we're just going to ask at every size, how many bursts do we see per year that are that value or greater? And so I'm going to show you next what we saw. Well, I'm going to show you some distributions next. So let's consider a distribution that might exist in the galaxy. So this is intended to be the plane of the galaxy. I mean, this is a proposed possible distribution. Most things that you see in the galaxy, they have a scale height. They're confined to some distribution that peaks in the plane of the galaxy, and it diminishes as you go farther away, some scale height. And so we're just proposing, and we don't know what that scale height is here. So let's just take some examples of, let's suppose we're measuring, we don't know where our sensitivity really is. It could be only measuring out to where the red arrow points to, or it could be measuring where the blue arrow points to. Look at the two cases, the galactic and nearby. So we're at the center here where the star is. So now if we are measuring this case, as we go out, everything is homogeneous, nothing's falling off. So it should look isotropic, as it does for us. And because everywhere we go out in increasing radius from the center out to R sub s, we pick up more sources, but they're dimmer, we should see a -3/2 power law. So this is one case. The other case, the blue case, we're seeing out much greater to a point where the sources are not homogeneous or falling off as they get further away. We should start to see anisotropy. We're seeing, as you go farther away from us, we're not seeing as many sources. In the same sense, as we're getting farther away, the number we're picking up as a function of radius is decreasing. So these are two possibilities. We either see isotropy and 3/2 power law, or anisotropy and homogeneous. So we already know this case is ruled out because we don't see this case. So the question is, do we see a 3/2 power law? And we don't. Now this plot was made within the first year of the mission. So here's log of 1 is 0. This is a rate of 1 per year. And we can't reach that point. We haven't been up long enough. So I mentioned before the Pioneer VS orbiter. It had a burst detector on it, been up for 10 years. So here's one burst in 10 years at this line. And so they were following a -3/2 power law, but they can't detect the really dim bursts. So we laid the data on top of each other. Here's a 3/2 power law, just offset for visibility. And what you note, and here's our sensitivity limit. We see bursts all the way down to this intensity. What you notice is it not only falls below 3/2, in this whole last factor, this power law here, this last decade, we don't see any burst. We're seeing all the bursts that exist. We never see bursts just above our threshold. It's the same number we see at this level of 10 to the -7 in those units, down to the edge here, down to our limit, is flat. So we're seeing every single burst that exists. With a small 20-inch detector, I think that's really remarkable. So with this 20-inch detector, we're seeing all the bursts in the universe. It's just really striking. Gives me chills still. And so the rate is about 1 per day from all the galaxies in the universe. And I'm taking a step ahead here because I still haven't told you what is the actual distance scale. It's beyond our galaxy, but how far into the distant universe, early times, is it? I haven't shown you that yet. I'm about to get to that point. So the breakthrough happened in 1997. There was an X-ray satellite, Beppo-6, a Dutch-Italian collaboration. First of all, that's kind of striking. That's like a US-French collaboration. They're different cultures, so I think it's remarkable that they even had such a satellite. So there was a Dutch astronomer, Jan van Paradijs, who got that information from the Dutch, and he had some telescope time in the Canary Islands, the Palma telescope, and just at that point, it managed to get some observations in the optical. See, the problem with gamma ray bursts is the resolution, you only get things to within a few degrees location. And there's so many objects within a few degrees, you can't find counterparts. It's really a problem with the ability to make progress in gamma ray astronomy is the resolution. But now you have observations in the hard X-ray range. Maybe you get an optical measurement. Maybe you can find an object. Maybe you can get a redshift. So this is what you've been trying to do for a long time, is see, long after the event is over, can I get a location? Can I get a redshift? Can I get a distance? That's what people are striving to do for a long time. And so what they managed to do is get the first afterglow pictures. So they have, this is after, see, 3 days later, they made the first picture within a few hours. And 3 days later, it was much dimmer. And this is like arc-minute resolution. This is the X-ray images taken from that satellite. And so 21 hours later, they made the optical observation. And the man that did this is Jan van Paradijs, and we knew him so very well. He died of cancer just 2 years later at the age of 53. And this is the most amazing scientist I ever met in my life. He was of such a caliber. These are the kind of people that they go everywhere in the world would have the best data. We had much more data of the best quality for gamma ray bursts than anywhere else in the world. So of course he came there. He didn't come as a guest investigator. He spent half his time there, University of Alabama in Huntsville, and half the time back in Amsterdam. He actually ended up marrying one of our scientists, our Greek scientist, Christos Koveliotou. You can tell it's from about 1993. You can see the old VAX-AMS terminal. I guess he liked sticky notes quite a bit. That's the calendar we use to put people's names on, who is going to be handling the gamma ray burst on a particular day. I think he's holding a 3.5-inch floppy in his hand. This is a very old picture. I think you can see the kindness in his eyes. This is a man, we go to scientific meetings. First of all, he wrote a He edited a book on X-ray binaries and wrote several chapters in it, including a catalog of all known X-ray binary sources. There are about 200. But he had all that information in his head. So you go to a scientific meeting, and somebody would have some new result about either a new object or something new about a previously observed object. And Jan would get to the floor and say, well, in light of your new results, these other objects, I think I can see a mechanism here. This is the nature of what these objects are, what the causes of these things. So you have just in real-time science a new theory. Now, many people, some people, might have had a thought like that, but they would be afraid to express it because they want to make sure they could publish it. But there was so much respect for him that nobody would step in front of his ideas. So he was just a lovely man, human being, a brilliant scientist, and it's such a loss, something like that didn't have a long life. He was publishing papers with his graduate students within a couple of weeks when he died, so it's such a loss, I still feel it. So then his student, Galama, actually made these optical observations, and we see that here. If you're going to be an astronomer, you have to be excited by little black spots on negative film. So here's the observation. It's near an M dwarf, the optical transit, OT, and then 8 days later, it's gone. So you can't imagine, since you're trying to understand gamma ray bursts, certainly since 1973, to actually finally see optical measurements that you're tying it to. Optical is a place you can actually make some headway because you can get Doppler shifts and red shifts. This is really thrilling to the community. It's such a long time in coming. And so then 6 months later, there was an observation made by Hubble, and they managed to see a very, very dim galaxy. You see here's the background intensity, these dots everywhere, and this is just barely above background. Sure, there's an enhancement here. But it was too dim to actually get a redshift. You don't have the distance. But then, luckily, a few months later, in May, there was another burst, and they got a redshift of 0.7 and got a distance of 8 billion years. So finally, after 30 years, we know the distance to the gamma ray burst and thus the energy. And if it was isotropic, it would be like 10 to the 50 ergs. Now, the sun puts out in its whole 10 billion year lifetime about 10 to the 50th ergs. So this is an extremely large amount of energy. Now, what it likely is that they're beamed. So they're probably 10 to the 51 ergs. That's still 10 times the amount of energy the sun puts out in its whole lifetime. Nothing more energetic than a gamma ray burst. So multi-wavelength observations are always very important. You want to constrain theorists. It might be relatively straightforward to come up with several models to produce a gamma ray burst, but if you look in different energy ranges, they're found now in X-rays, optical, radio, or at various time scales. That's your chance to maybe find a model that actually explains the whole range of emission, different wavelengths, and maybe it's the correct model. We're always stuck at looking at data from a great distance. You can't go there, you can't do experiments. So extending into multi-wavelength observations is a way to go. So an example of a multi-wavelength observation is this an X-ray measurement actually from the SWIFT satellite. And you can see the actual burst is in the first couple hundred seconds here. If you're a factor of 10 or more than 20 above the level here. And then over the next 35 days, it actually, intensity changes. There's different slope changes. This is a log-log plot, so it's a power law dependence, and it changes at various points. What's happening here? Well, if you look at the third lecture, I'll tell you what the thought is about that. Then there's only two cartoons having to do with gamma ray bursts, so I have to use them, of course, one of them in this lecture. This is done by Kevin Hurley. He was heavily involved with the interplanetary network, producing some of those timing curves that you saw earlier. So that's a dinosaur, Tyrannosaurus Rex, saying, uh-oh, here comes a gamma ray burst. So we have one gamma ray burst per universe per day. That's what we're observing. And there's thought to be 10 to the 13th galaxies in the universe. There's only 10 to the 5th galaxies at the distance of the nearest gamma ray burst, which is only 100 million years away. Okay. And so we might have one burst per million years per galaxy, and perhaps one within 3,000 years and 100 million years. Could this produce extinction events? When you start presenting information about gamma ray bursts among scientists, not that many of them think about personal risk, but you're talking to other mortals that have science interests. It's quite common to say, well, could this kill us? So there are objects that are even closer. There's a couple of there's a pulsar and two neutron stars that are only half a kiloparsec away. Parsec is 3.26 light years. And within a billion years, they might be able to produce a gamma ray burst. and it produced the equivalent of 10 to the fourth megatons of TNT, the whole worldwide nuclear arsenal. So the world's a dangerous place. On some time scale, they think something's going to get us all. So what effect would that have if something was nearby? It would completely destroy the ozone layer in a very short time. And the gamma rays that are produced are stopped in the upper atmosphere. They ionize the nitrogen, producing nitric oxides, which catalyze ozone destruction. It would take the sun a long time to regenerate the missing ozone. So the UV radiation would reach the ground and produce, it's thought to be at 10 parts per billion, the level we are, and actually dissolve in the oceans. And it's a possibility that could cause some damage to life. In fact, there's a couple papers, one in Nature in 2003, one in Astrobiology in 2016, suggesting the Ordovician period, 450 million years ago, fits with the gamma ray burst occurring 3,000 light years away if it primarily exposed the South Polar region. There were quite a few different species that were wiped out. I say it's very speculative. That's not the only reason they could have been damaged. So in summary, we've learned gamma ray bursts are extragalactic from the early universe and do not repeat, releasing at least 10 to 51 ergs of energy with durations of 10 milliseconds to hundreds of seconds. We're detecting all of them that are beamed in our direction, and they come from the early universe as early as 625 million years after the Big Bang. That's when the first galaxies are forming, with redshifts as large as 8.2. So thank you.